We are on chapter 3, section 4, In Search of an Octet, part 2. So we're going to talk today about covalent bond formation. But before we do that, I want to do a quick little review about ionic, and then we're going to talk about covalent. So one of the things we talked about was, right, if you had sodium and chloride, the sodium is going to give up an electron, chlorine is going to take that electron, and then you're going to have these ions that are then, let me put a little plus sign on my sodium, are attracted to each other. And so when we say you have sodium chloride, we write that formula sort of like this, sodium chloride. But it's telling you that you have one sodium ion for every one chlorine ion. But when you put salt on your food, are you only putting one atom of chlorine and one atom of sodium on your food? No, you're not. There are a lot more atoms there. And so when you really think about the structure of an ionic solid, what you're actually going to see is this repeating pattern of one chlorine for every one sodium. And it's really chloride and sodium ion, right? And so what you would see is something sort of like this, right? So we go sodium chloride, sodium chloride, sodium chloride, and over and over and over and over and over again, right? And, you know, what you end up with, let's see, copy, we'll paste this again, right? Here's a whole nother row. And this is exactly what an ionic compound looks like. So the formula that we give for an ionic compound is basically the ratio of atoms within that compound. And so it's a lattice. It looks like a pattern. Do you see how beautiful that pattern is, right? That's an ionic compound. And this could go on for as big of a molecule as you have, right? You know, that inside of your salt shaker, right? It'll go on and on and on. You could have a salt block, you know, like if you ever have a horse, you know, you get them salt blocks and they're huge, right? So it can go on and on and on in 3 dimensions until you get to the size of whatever you are, right? Covalent compounds are different. Covalent compounds occur as molecules. So I want you to think about water, right? If we talk about water, we know that water's formula is H2O. Does that mean that we have the similar shape of our molecule as we do in an ionic solid? And it's not. When you have water, we know that that means for every one oxygen, you are going to have a bond to 2 hydrogens. And if I had a glass of water, that means that I'm going to have a lot of these individual, I could move this around, this individual molecule, right? It's all the same. It's all water. But they're not all kind of interconnected the way a ionic compound is. A covalent compound, each one of these things is a molecule. You can't have a molecule of an ionic compound. It doesn't work, but you can have a molecule of a covalent compound. So it's important to understand the structural difference between an ionic solid and a covalent, or ionic compound and a covalent compound. So keep that in mind as we go on and we talk about covalent bond formation. So when we talked about ionic, we talked about giving and receiving electrons. Well, in covalent bond formation, no one actually completely gives anything up and nobody takes anything completely. It's all about sharing. It's sharing those valence electrons in order to achieve an octet. And whenever electrons are shared, you have the formation of a covalent bond. And so those shared valence electrons no longer belong to only one atom, they belong to 2 atoms. And so any 2 atoms that are sharing electrons are covalent compounds, or what form the covalent compound, the bonds inside of them. So the smallest unit of a covalent compound is a molecule. Like here, we had 1 molecule of water. We don't see that in ionic. We only see molecules in covalent. So how do we know how many bonds anything's going to form, right? Why does water only form 2 bonds, right? Well, you have to understand the electron configuration of the valence electrons and that they want to get to an octet. So one easy way to start to look at that is to use the electron dot symbol. They call this Lewis dot because it was the chemist who initially really discovered that electrons are shared in the covalent bond. And so our electron dot symbol is you take the element's symbol and you put a dot for each valence electron. I know it's a challenge, but I know you can do it. Okay, so let's try one that's not on here. Let's try sulfur. So if I have sulfur and I want to draw the electron dot diagram of sulfur, I need to go to my periodic table. I need to find sulfur. Sulfur is number 16. It's an S. So sulfur is in group 6A. That tells me that I have, so sulfur is group 6A. That tells me I have 6 valence electrons. So I'm going to use a dot to symbolize each of them. 1, 2, 3, 4, and now I'm going to double up, 5, 6. Does it matter which ones are paired, which ones are by themselves? No, it doesn't matter. So long as you do them individually and then you pair them. So let's do another one. Let's do phosphorus. Phosphorus is number 15, so just go back 1. So it's in group 5A, and so we know we have 5 valence electrons. So 1, 2, 3, 4, and then you can pick any one you want and pair it. Okay, so here we're just giving you some more examples. Hydrogen only has 1 valence electron, so we put 1 dot. Carbon has 4, but notice that they're all 4 by themselves. I do not want to draw carbon if I have 1, 2, 3, 4. That's not right. Always leave them unpaired, then pair them. So carbon has 4, so it gets 1 dot, but nitrogen has 5. So we're going to give nitrogen 1 dot all the way around on each side, and then we're going to give one side a second dot. Okay, and so on and so on. Okay. So when we're doing an octet, an atom is going to share its unpaired electrons. So when we talked about unpaired electrons over here, right? How many unpaired electrons do we have in sulfur? Which ones are unpaired? I have 1, 2 unpaired electrons. So these are the electrons that are going to participate in the covalent bond. These 2 that are basically together are good. You can leave them alone. So sulfur has 2. Phosphorus has 3 electrons that can participate. Hydrogen, right, has 1. Carbon has 4, unpaired. Nitrogen has 3 unpaired. Oxygen, 2 unpaired, right? Fluorine, fluorine's only got 1 unpaired. So this tells you how many electrons can participate in a covalent bond. They have to be unpaired in order to participate. So to complete its octet through a covalent bond, an atom must share its unpaired electrons with another atom. So we call a shared pair of electrons a bonding pair, or simply a bond, right? So let's take a look at our example here. We have chlorine. Each chlorine atom has 7 valence electrons. And we know that each of these chlorine atoms has 1 valence electron that could be shared, right? So what happens is, let me try a different color, right? That this electron here spends half of its time with this atom and half of its time with that atom. And that makes this chlorine atom happy because now he's got 8, but the other chlorine's not happy. So this electron here is going to be shared half the time as well. It's going to spend half the time with one chlorine atom and half the time with the other chlorine atom. So a lot of times the way we draw this is to put the 2 shared electrons in between the 2 atoms. And so they share a side, which means they share those 2 electrons. If you have 2 electrons, Now, do you have an octet? Well, let's count, right? Let's count our electrons. We have 1, 2, 3, 4, 5, 6. Now those shared electrons you count for both. So I have 7, 8. So this chlorine atom is happy. Let's try the other one. 1, 2, 3, 4, 5, 6, and again 7, 8. Because they're shared, they count for both atoms. And so now this one's happy. Both chlorine atoms are happy because they're each sharing an electron with each other. So there's one more way that you can draw this. So instead of drawing 2, we draw 1 and we do it as a line. And so when you're counting, right, I a lot of times do this, 2, 4, 6, and then this makes 8. And the same thing for our other atom. 2, 4, 6, and we're going to count this again, 8. So both atoms have 8 valence electrons and they're happy. So this bond is our shared pair of electrons. That's a covalent bond. The dots that are by themselves, well, that are 2 by themselves, we call those lone pairs. So you have to understand the difference between a bonded pair of electrons and a lone pair of electrons. So each of these carbon atoms has 1, 2, 3 pair of lone electrons and 1 pair of bonded electrons. Okay. All right. So now each of the atoms has an octet and they are both super happy. So if we look at our electron dot diagrams again, we're going to see how many covalent bonds we can form with each atom. So look at hydrogen. Let's say we have another hydrogen atom. So here's my hydrogen, and I have another hydrogen, and it's got 1 atom. Hydrogen is special. It doesn't want 8 electrons. It only wants 2. So if we have 2 hydrogen atoms, those 2 hydrogen atoms can each share their electrons, right? So how would we write this? We would put the 2 electrons between the 2 atoms because they're sharing it. And now we draw that as a straight line. So hydrogen wants to form 1 bond to complete its octet. All the other elements are going to want to form 8. So let's look at another example. Let's look at, for example, oxygen. So oxygen has 1, 2, 3, 4, and I shouldn't put it on that side, but okay, 6, right? 1, 2, 3, 4, 5, 6. So what's oxygen going to do? Well, it wants to share with more of its electrons. So this one has a lone pair here, a lone electron here and a lone electron here. This one has 1 here and this one has 1 here. So how many bonds can it form is how many electrons are by themselves. So oxygen will form 2 bonds, whereas hydrogen could only form 1. So let's look at some examples, right? Carbon's really cool. Carbon, right, has, if you look, is in group 4A, element number 6. It has, because it's in group 4A, 4 valence electrons, right? If it has 4 valence electrons, my picture is covering this. There's my electron dot diagram. I have 4 valence electrons. So carbon is going to have to form 4 covalent bonds to complete its octet. How's it going to do it? Well, everything we've talked about so far is a single bond. So what carbon could do is carbon could, let's say, interact with 4 hydrogens. So we'll come up here and we'll say hydrogen has 1. Here's another hydrogen, that's 1. Here's another hydrogen, and here's another hydrogen, right? And so we can turn these bonds these are shared things into bonds, right? So we turn these into bonds because they're sharing those electrons. So now I have carbon with 4 single bonds bonded each single bond to a hydrogen. Does carbon have a valence, an octet in its valence electrons? Yes, because the bond counts for 2. So I go 2, 4, 6, 8. Carbon's happy. How about hydrogen? Is hydrogen happy? Well, each hydrogen only needs 2. So look at hydrogen. Does hydrogen have 2? Does this one? Yes, because it has 1 bond, so it has 2 electrons, so it's happy. How about the next hydrogen? It's got 1 bond, it's happy. The third has 1 bond, so 2 electrons. And the last one, same thing, 1 bond, 2 electrons. So everybody has a complete outer valence shell. The other way that this could happen is that carbon can form what's called a double bond. In a double bond, the carbon is sharing more than 1 electron with another atom, right? So let's say we have hydrogen here and hydrogen here. I can make another double bond, let's say with another carbon atom, right? And I can complete the octet. So remember, each line is a bond and counts for 2 electrons. So if each bond is 2, I'm going to count around carbon 2, 4, 6, 8. Carbon's happy. Let's check this carbon. 2, 4, 6, 8. So each of those carbon atoms has a complete octet and is happy. The other thing that can happen is instead of having a double bond and 2 singles, right? What you could actually end up having are just 2 double bonds. So a double bond on this side and a double bond on this side. Each line counts for 2 electrons. So that's 2, 4, 6, 8. We got a complete octet. And the third way you could do that is with 1 single bond. So that's 2. And then a triple bond. So that's 2. Oh, I already counted 2. 2, 4, 6, 8. So we have a complete octet. Remember, a line counts as 2 electrons and they're being shared. Okay, so how do other elements do it, right? We talked about carbon. We said because carbon has 4 valence electrons, it needs to make 4 bonds. And there are different ways that it could do it. It could do 4 singles. So this is 4 single bonds. It could do 2 single bonds and 1 double. Could do 2 double. It could do 1 single and then 1 triple. Either way gets you 8 valence electrons. Look at nitrogen. Nitrogen has 3 unpaired valence electrons. It has a total of 2, 3, 4, 5 valence electrons, but not all those valence electrons are available to create bonds. Only the ones that are unpaired. So here's an unpaired, here's an unpaired, here's an unpaired. So these are the 3 that are available for bonding. You're not going to touch that lone pair on the top of the nitrogen. You leave it alone because it's got a buddy. It's good. So you just worry about the 3 unpaired electrons. And so it can make 3 bonds. So you can make a total of 3 bonds. How could you do 3 bonds? 3 different ways. 3 singles, a single and a double, or just a triple, right? Okay, oxygen. If we look at oxygen, oxygen is in, okay, group 6A, so it has 6 valence electrons. When you draw your electron dot structure, what you're going to see is you have 1, 2 electrons that are unpaired. And so you can create 2 bonds with oxygen. There's only 2 different ways that you can do that. You could do 2 singles or a double. Fluorine. Fluorine is in group 7A, so it has 7 valence electrons. But when you do your electron dot diagram, what you're going to see is you only have 1 unpaired. And so fluorine can only make 1 bond. And the same is true for elements that are in the same group. So oxygen is one example, but sulfur is another example. Sulfur can also make 2 bonds, right? Chlorine is in the same group as fluorine. So fluorine can only make 1 bond, chlorine can only make 1 bond. So elements that are in the same group can do similar bonding because they have similar valence electrons. Okay, so whenever we write covalent compounds, we're going to write what's called a molecular formula. A molecular formula identifies all the components inside of a molecule. So just like we said H2O, every single molecule of water has 2 hydrogen atoms and 1 oxygen atom. Glucose or sugar has the formula C6H12O6. So that tells us in every single molecule of glucose, we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So molecular formulas don't reduce the way ionic compounds do. Remember when we drew it and we said it's just a ratio? Well, molecules are not ratios. They're actually written the way that the compound is organized. So you see your C6H12O6, we could reduce that, but we can't because it's a molecular formula, because this is the molecule of glucose. If you change the formula for glucose, you would be making some other substance that's not glucose. So you can't reduce the formula. So be careful with that. And the formula doesn't tell us about the structure. We have to be able to draw the structure, and I'm gonna show you how to do that. So here's an example. We kind of already talked about this, right? Carbon. Carbon, when we draw its electron dot, Lewis dot diagram, what we're gonna say is carbon, and I'm covering everything here. So here's carbon. Carbon has 1, 2, 3, 4 valence electrons, right? It's in group 4A. So it has 4 valence electrons. So carbon is going to have to make 4 bonds to be happy, to get an octet. So if you combine carbon and hydrogen, each hydrogen atom is going to make a bond with carbon because each hydrogen has 1 electron that it can give, right? Hydrogen, here's its 1 to give. Hydrogen, here's its 1 to give. Hydrogen, here's its 1 to give. So now we have our complete octet. And so when we change those dots into lines, see how we each have a line here, and a line here, and a line here? We call this a Lewis structure. And so this is a way to draw how atoms are arranged in a covalent compound. So when you're doing this, this is the way the book tells you. I'm going to teach you a slightly different way, but I'll show you both ways. So you're going to draw the electron dot symbols. Then you line up the atoms and you see what pairs, and then you confirm that you have complete valence shells. And so it's just making sure that those lines are from 2 shared electrons. Okay, and it can be a little bit confusing at first, but we're going to go through a bunch of examples, so don't worry. All right, so we're going to be able to draw them and we're going to be able to name them. So when you're naming covalent compounds, it's different than ionic. So you have to be able to recognize what's an ionic compound and what's a covalent compound. Well, when we talk about covalent compounds, what we're really talking about is a non-metal plus a non-metal, right? Remember how, and when we were talking about ionic, if you're ionic, you are some kind of a cation and an anion. Let me not put a plus there, let me put an and. And a lot of times that plus was a metal and the negative was a non-metal. And you could have polyatomics in either place, but generally ionic is metal and a non-metal, whereas covalent is a nonmetal and a nonmetal. So it's important for you to be able to recognize that. So when you're naming a binary compound, binary means two. Bi is two. So you have two atoms. Two elements, excuse me, not two atoms, two elements. You look at the formula and you name the first element in the formula. Then when you look at the second atom, you're going to end it in IDE. And then you need to say that'll tell you what two atoms you have, but it won't tell you how many of each, because we don't have charges the way we did in ionic compounds. And so what we do is we use a prefix to say how many of each that you have. So let's take our water, right? A lot of compounds have common names and they also have scientific names. So scientifically, how do you say water? Well, I'm going to name the first element in the formula. What's my first element in water? Is hydrogen, right? Name the second element in the formula and change the ending to IDE. So this is oxide. And now I need to designate the number of each element present using one of the Greek prefixes. Greek prefixes are mono, di, tri, all those. And I'll kind of give you a list. I think your textbook gives you a list. So how many hydrogens do we have? We have two. So mono is one, di is two. So this is dihydrogen. And then we need to say how many we have of oxygen. Oxygen is only one. So this is dihydrogen monoxide, MON. So dihydrogen monoxide. So the next time you need to go get a drink of water, you can instead say, oh, I really need a drink of dihydrogen monoxide. You freak people out because everything has a scientific name. We just have some common names that we say, right? Okay. So here's your, oh, I did have a table. Ha ha ha. So you have mono is one, di is two, tri is three, tetra is four, penta is five, hexa is six, and hepta is seven. The only exception is if it is the first element, and it has only one atom, you don't put mono. So if I had something like CO, I would say that's carbon, right? And then I want to say, I just name my first element, and I name my second element, and I'm going to end it in ide. So that's oxide. So carbon oxide, but now I need prefixes. I only have one carbon, but it's the first element, so I'm not going to add anything to it. So I have carbon, and then I have one oxygen, so I'm going to say carbon monoxide. So CO is carbon monoxide. CO2 is carbon dioxide. Dioxide, right? But this carbon only has one. So we don't say monocarbon monoxide. We just say carbon monoxide. So if you just say the name, it's assumed that there's only one there. It's kind of like not writing the one in the formula. Same sort of deal. Okay, so whenever you're looking at trying to name something, you have to first identify, is it ionic or is it covalent? If it's ionic, we have a metal and a nonmetal. Remember, your metal's positive, your nonmetal's negative. If it's covalent, you're going to see two nonmetals. If it's two nonmetals, use your Greek prefixes and your second, you're going to end in IDE. Okay, so be careful with that. Then if it's a metal and a nonmetal, you know it's ionic. And so if it's a main group metal, then you don't need Roman numerals, you don't need Greek prefixes. You're just going to end, you're going to put your metal name, then you're going to put your non-metal, and you're going to end it in IDE. Same thing if it's a transition metal, right? Then you're going to use those Roman numerals, and you're going to end the non-metal in IDE. So you notice everything ends in IDE. Okay, so let's go do some practice. Go do some practice. Here we go. Okay. Draw the correct Lewis structure for each of the following compounds. I'm going to show you the book's way, and then I'm going to show you my way. I love my way so much more, but we'll do it, okay? So phosphorus, PCl3, that's the first thing we need to do. So if you go to your periodic table, and I'm not going to keep switching back and forth, I'll just tell you what you should be looking for, right? So phosphorus is in group 5A. So how many valence electrons do you have? You have 5. We're going to do them singly, and then we're going to pair them. So how many electrons do we have possible to participate? 3 possible electrons can participate in a bond. All right, and then we have Cl3. So if I draw one chlorine atom and I give it, let's see, chlorine's in group 7A, so I'm going to give it 7 valence electrons, and I'm going to leave them unpaired, and then I'm going to pair them to where I have 7. What I can see is that chlorine has 1 valence electron that it can create a bond with. Phosphorus has 3. So I'm going to need some more chlorine atoms. How many more chlorine atoms do I need? It's PCl3. I'm just showing PCl, so I need 3 more chlorines. So I need 1, 2, 1, 2, 2, 1. Okay, and then I'm going to draw myself another chlorine. Okay, and so here are my electrons that are available for bonding. So what you're going to do is you're going to turn, whenever you have a pair that's going to bond, here's a pair that's going to bond. We're going to connect them and turn them into a line. Here's another one that's going to bond, and here's another one that's going to bond. So we have 3 single bonds, right? So that's our structure for PCl3. I'm not really a fan of doing it that way. I like to think about how many electrons does the whole compound need, how many does it then need to share in order for everybody to get a complete octet, and then how many are left over. So I do this thing called needed, available, shared. This is just a different way to do it. So you could do it either way. So how many electrons do we need? Well, if we have PCl3, we have 4 atoms, right? So we have phosphorus is 1, chlorine we have 3, we have 4 atoms, and each of those 4 atoms needs 8 electrons, right? So how many total electrons do we need in the whole molecule? We need 32 electrons. But how many are actually available, right? Everybody wants an octet, but you don't have enough electrons to make an octet. So let's see how many electrons are actually available in the molecule. Well, our phosphorus, we have 1 phosphorus. It has 5 valence electrons. We also have 3 chlorine atoms, and each of those chlorine atoms has 7 electrons available, right? So that gives us a total of 26 electrons. Let me scooch this over so it lines up. Okay. All right. So we need 32, but we only have 26. So if we subtract these two, so if I subtract these two, what I'm going to figure out is how many I need to share. I need to share 6 electrons in order for everybody to have a complete octet. So how many bonds am I going to have? How many electrons are in each bond? There are 2. So if I take this 6 electrons, I divide it by 2, that tells me I need 3 bonds. Okay. How many do I have left over? I'm going to take my available minus my shared. So my available was 26 electrons and my shared were 6 electrons. So I have a total of 20 left. So How am I going to use that to draw my structure? I know I have phosphorus, and I know I have 3 chlorine atoms, right? So I only can make 3 bonds, and I have 3 chlorines. So I'm going to do a bond to each of them. And then I know I have 20 left. So I'm going to place my electrons to complete my octets on my surrounding atoms. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now where do I put the other 2? 19, 20. Does everybody have a complete octet? Phosphorus has 2 on top. That's 2, 4, 6, 8. So it's happy. I want to erase it. Chlorine, 2, 4, 6, 8. Chlorine's happy. And all the chlorines are the same, so they're all happy. So it's good. You can use either way. It does not matter to me. Doesn't make a difference. H2SE is used in the production of semiconductors. Let's see. So let me move this. I want to take the whole thing because it's 2 of the same diagram that we did, right? So we'll just kind of shrink it. Maybe we'll shrink it. Ooh, me and technology sometimes. Okay, let me just delete it. Okay, so H2SE. Okay, now you have to be careful with hydrogen because remember, hydrogen does not need a complete octet. It just needs a complete outer valence shell, which is only 2. So I'm going to do my needed available shared. All right, so I have, how many do I need? Well, hydrogen, I have 2 hydrogens, and hydrogen only needs 2 outer electrons. Then I have selenium, Se. Se is going to need 8, so I have 1 of that, and I'm going to need 8. So 2 times 2 is 4, plus 8 is 12. Available, how many are available? Well, I have 2 hydrogen atoms, and each hydrogen atom has only 1 electron to give. So then we can take selenium. Selenium, if you look in the periodic table, Se is in group 6A. So it has 6 valence electrons. So these are my available. So I have 8, I only have 8 available, and I need 12 electrons to make everybody happy. So in order to fix that, we're going to share some. So we subtract the 2. 12 minus 8 is 4 electrons that we need to share. Divided by 2, because that'll tell us how many bonds we need. So we need 2 bonds, right? So now we're going to look at what was available minus what we shared. We had 8. We shared 4. That's going to give us 4 electrons left. Okay, so I'm H2SE. So I'm going to put Se, and I'm going to put my H's. I only can make 2 bonds. So make 2 bonds. I have 4 electrons left. Well, my hydrogen has complete outer valence shell. So you can't give hydrogens any electrons. They're complete, they're good. So you have to put the electrons on the selenium, on the Se. And so I'm going to put 1, 2, 3, 4. And that's your electron dot diagram, right? Okay, I obviously did not leave enough room for these. All right, so I'm going to go ahead and erase, and I think erase, clear, cut, whatever it is. Okay, let's try a different color so we don't overlap. All right, CS2, an insecticide. So let's do our needed, available, shared. Carbon and sulfur both need 8. So we have 1 carbon that needs 8. We have 2 sulfur that needs 8. So how much does that give me? I need a total of 24 electrons. How many do I have? Well, in my carbon, I have 4. So I have 1 carbon atom and it has 4. I have 2 sulfur atoms, and each sulfur atom should have 6. So how many available do I have? I have 16 available, but I need 24, so I'm gonna have to share some. So subtract the 2, you get 8 electrons. Divide by 2, that tells us we're gonna have 4 bonds, right? So we had available 16. So if we take our available minus our shared, this is what's gonna be left. So we had 16 electrons available. We subtract our 8 electrons from our shared bonds and we get 8 electrons left. Okay, so let's put them in a structure. So if we have carbon and we only have 2 sulfur atoms, I'm gonna put them on either side. Now, I have to make 4 bonds, but I only have 2 elements that carbon can interact with. So how am I gonna make that happen? I'm gonna give a double bond between each carbon and sulfur. So they're each sharing 2 electrons. So it's like you have an electron here, an electron here, an electron here, and an electron here, and here, and here, and here, and here, right? Now I have 8 electrons left. Where do I put them? I can't put them on carbon because if I count carbon, I have 2, 4, 6, 8 electrons. So I can't put my leftover electrons on the carbon. I have to put them on sulfur because if I count sulfur, I have 2, 4, and that's it. 2, 4, and that's it. So what I want to do is I want to put them on sulfur. So I'm going to put them 1, 2, 3, 4. 1, 2, 3, 4. And that's it. And it doesn't really matter where you put your dots until we get to molecular 3-dimensional structure. We're just drawn in 2D here. So you can put them on any side. It's not a big deal. Okay, D, C2H6 ethane, a minor component of natural gas. Now, let's do this one the book's way. It doesn't really matter how you do it, okay? So if I have carbon, I have 2 carbon atoms, and I know that each carbon atom has 4 valence electrons, and then I know I'm gonna have 6 hydrogens. So usually your carbons are gonna be connected together if you have multiple carbons. And so what I can basically do is I can scooch this over and I can say, okay, they're gonna share an electron. And I'm gonna turn that into a bond. Now, I have 3 available electrons for bonding on each carbon, and I have 6 hydrogens. That works out pretty well, right? So I have a hydrogen, and it has an electron it can share. A hydrogen, and then a share, hydrogen, and a share. We just keep doing this, right? And so now we're gonna change those dots into bonds. So let's erase those dots, and we're gonna turn them into bonds. Okay, and so that gives you your structure. Either way is going to work. Does not matter to me which one you do. Okay, so we have some more. Draw the correct. So SiO2. So if we look at silicon on the periodic table, silicon's in group 4A. So Si has 1, 2, 3, 4 valence electrons. O2, oxygen, if we look on the periodic table, has 6 valence electrons. So 1, 2, 3, 4, and then we're gonna pair them up. We're gonna say 5, 6, right? Maybe I can make that dot. Okay, and then another oxygen, 1, 2, 3, 4, 5, and 6. So how are we gonna make all of the atoms happy and have an octet? Well, if we move our oxygens in to where we're sharing these 2 electrons right here, and we're gonna turn those 2 electrons, because we're sharing them, into a bond, right? Let's do that with the other oxygen as well. I'm gonna move him in, and we're gonna convert those shared pair of electrons into a bond. Is everybody happy? And the answer is no, not everybody's happy. I have 2, 4, 6, 7 on my oxygen, and my silicon is 2, 4, 5, 6. So nobody's really happy. So what we're going to have to do is we're going to have to move in some more electrons and make some double bonds. Hello. Okay, so if I move, let's say, this electron, and I take him and I turn it into another bond, right? So let's do that. Let's take one electron from each atom, one unpaired electron from each atom, and turn it into a bond. And let's do the same thing over here. We're going to take our 2 electrons and we're going to turn them into a bond. So what do we get? Let's count silicon in the middle. 2, 4, 6, 8. Looks good. Then let's check our oxygen. 2, 4, 6, 8. You have a complete octet. Let's check our other oxygen. 2, 4, 6, 8. Yes, we have a complete octet, so we're good. You just don't want to leave your structures with all these numbers all over them, right? Okay, so that was A. That's A. B, C2H4. C2H4. And whenever you have just carbons and hydrogens, it's usually really easy because the number of hydrogens is usually divided between the carbons equally. So if you have 2 carbons, right, I'm going to give each carbon 2 hydrogens. So, right. So now I'm going to draw in my electron dot. I got 1, 2, 3, 4. 1, 2, 3, 4. Now I'm going to draw in my hydrogen electrons. Here's 1 for this hydrogen, 1 for that hydrogen. And so what you can see is you're going to now make a bond, right? You can make a bond here, 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 and here. So let's go ahead and do that. Let's turn these into, whoops. Shouldn't have drawn it so small. Okay, so let's turn those into bonds. Now, count up your electrons. It doesn't work, and we haven't connected our carbons yet. So let's go ahead and connect our carbons. We're going to say that these 2 carbons are going to share these 2 electrons. So we're going to turn them into a bond. So we did that. But is everybody happy? Count either carbon. Each bond is 2, 4, 6, 7. That doesn't work. So what we're going to do is we're going to take each of the carbons, each of the carbons electrons, see if I can zoom in, make this a little easier, and put them here. Take this one and put it here. Now they can participate in sharing. So each carbon is going to share each electron, and we're going to turn that into another bond. And so what we end up having is a double bond. Shift this up a little bit. Okay. So the carbons are connected by double bonds, and then the hydrogens are connected to the carbon by a single bond. All right, let's see. C, O2, molecular oxygen. Oh, I will tell you though, if you do the needed, available, shared, it tells you how many bonds need to be there. And so sometimes that's a little easier to do. So I'll show you, let me show you this one, needed, available, shared. Let's do this one both ways. And if you don't like it, you could just fast forward. Needed, available, shared. Okay, so I have carbon. I have 2 carbons, and they need 8 electrons each. Hydrogen, on the other hand, we have 4. And they only need 2 electrons each. So if you total that up, 8 and 8 is 16, and then 4 times 2 is another 8, 16, 24. Then available. So how many does carbon actually have? We have 2 carbon atoms, and each carbon actually only has 4 electrons that can participate. Then we have hydrogen. Hydrogen has 1 electron each, so we have 4 hydrogens times 1. So that's 8 plus 4 is 12. So we have to share 12 electrons. Divide that by 2, that gives you 6 bonds. I'm running out of room, 6 bonds, right? So if I do this, I said carbon, carbon, And then I'm going to give them each a hydrogen. So I need 6 bonds. If I do this, 1, 2, 3, 4, 5. Well, that would tell me I need another bond. And I can't make that bond with a hydrogen because hydrogen's got a full outer shell. So you just stick another one in there. So, and then you do your available minus shared. Well, I had 12 available and I shared 12. I got none left over. So I don't need to put any lone pairs anywhere. Either way is going to work. Okay. O2. We're going to do needed available shared. Let's do that. So O2, we have oxygen is our only atom. We have 2 of them. They need 8 electrons. Available, oxygen is in group 16, well, 6A. So we have 2 of them and they have 6 available electrons. So 6 times 2 is 12. 16 minus 12 is 4 electrons. Divided by 2 is going to be 2 bonds, right? So now available minus shared. So we had 12. We're going to share 4 of our electrons. We're left with 8 electrons. Okay, so what are we going to do with those? Let's try. So we have 2 oxygen atoms. We got to make 2 bonds. So where can you put the bonds? Only between the oxygen. So I put 2. Now I need to divide up my electrons so that each atom has an equal number of electrons. And so I'm going to go 2. I'm going to give them equally. Let's do that. So that's 2, 4, 6, 8. I used up my 8 electrons. Now let's count. 2, 4, 6, 8. Okay, I have 8 on that atom. 2, 4, 6, 8. It's happy. So that's my structure. So I'm good. So y'all can do it either way. All right, last one, last one. Let's do a different color. Let's do red. No, we just did red. Oh, okay. D, we're doing CH2O. This is formaldehyde. That's another common term. It's not the scientific term, but it's a common term. Okay, so when you have lots of different atoms there, you know your hydrogens are only going to be like outer hydrogens that can't bond multiple atoms together. So you know a lot of times carbon is going to be your central atom. And then I know I'm going to have 2 hydrogens and I'm going to have an oxygen. So I kind of draw my simple structure. And then you can do your needed available shared, or you can do your dots. It doesn't matter. So I know hydrogen only will have 1. I know carbon will have 4. 1, 2, 3, 4. Hydrogen's going to have 1. Oxygen, on the other hand, has 6 valence electrons. So I know we're going to share 1 with carbon. So that's 1, 2, 3, 4. Well, let's do it the other way. Let's do carbon, hydrogen, oxygen. Let's do where we do different colors so it's easier for y'all to see. Okay, so then this hydrogen has 1, this hydrogen has 1, and then this one has 1, 2, 3, 4, 5, 6. So what are we going to share? Well, we know that these 2 are shared between the carbon and the hydrogen. So we're going to erase them. And we are going to put a bond. So that's a bond. We know that these 2 are shared. So we can erase them and we can turn that into a bond. We know, if we move the oxygen in a little bit, that they're going to share those electrons. So we're going to erase them. We're going to draw in a bond. But is everybody happy? Nope, they're not. Look at carbon, 2, 4, 6, 7. That's not going to work. So what we're going to do is we're going to take this electron. Why do I keep doing that? We're going to take this electron right here, and we're going to move him in here. And we're going to take this lone electron on our oxygen and move him in here. Now we're going to create another bond. And so now we have a double bond. So we have carbon attached to hydrogens with a single bond and attached to oxygen with a double bond. And then oxygen has two lone pairs together. And that's it. Okay. And the last ones, we have to determine whether they're ionic or covalent. Okay. So this is super, super quick and easy. I know this is kind of a long video, but let's look at this. We have nitrogen and fluorine. Nitrogen is a nonmetal. Fluorine is a nonmetal. Nonmetal and a nonmetal tells us covalent, right? That's our condition. If you are nonmetal plus a nonmetal, you are covalent. If you are a metal plus a nonmetal, you are ionic, right? Or you could have a polyatomic plus a nonmetal, or you could have a metal plus a polyatomic. Either way is all of those things are going to give you an ionic compound. Okay, so let's do the next one. Fe2O3. Fe is a metal, oxygen is a nonmetal, so a metal and a nonmetal tells us ionic. CS2CO3. CS is a metal. You just got to go look on the periodic table. CO3, this whole thing is a polyatomic. So a metal plus a polyatomic is going to give us an ionic. Okay, let's see. Not too much. PBr3. P is a nonmetal, so nonmetal. Br is a nonmetal. Ooh, two nonmetals. That must be covalent. C5H12. Carbon's a nonmetal. Hydrogen's a nonmetal. Must be covalent. NH4OH. Oh, now be careful with this one. This one we didn't even say. We got two polyatomics. So you could actually have a third. You could have a poly plus a poly, POL, polyatomic, gives you also an ionic compound. So this one is also ionic. All right, SeO2. Se is a nonmetal, oxygen's a nonmetal. So a nonmetal, covalent, V-O-V-A-L, covalent, right? BAS, metal, Ba is a metal, barium's metal, and sulfur is a nonmetal. So a metal and a nonmetal, ionic. CBr4, C, carbon, nonmetal. Br is a nonmetal. That tells us that we are covalent. I could spell. OF2, O is a nonmetal. F is a nonmetal. What you'll notice is if you start with a nonmetal, it's going to be covalent. Hint, hint. Okay. So you should be able to do that. Be able to identify covalent and ionic. Okay. Oh, this is our last one, finally. Okay. So complete the table by supplying the missing name or formula for each covalent compound. So this is telling you it's covalent. So we have nitrogen dioxide. Remember, if it's just the name, all we do is assume that there's one of that atom. And then dioxide. So oxide is telling us oxygen, and it's telling us that there are two. Okay, so now we have phosphorus and chlorine. So we only have one phosphorus, so we can just say phosphorus. H-O-R, phosphorus. And then we have three chlorines, and our prefix for three is tri, so trichloride. Okay, the next one, silicon tetrafluoride. Silicon tells us there's only one silicon, there's no prefix on that. Fluorine is F, and then we have four of them because it's tetra, so the tetra tells us four. H2O, we did this one, dinitrogen monoxide, right? And that's water. Nitrogen trichloride. Nitrogen, there's only one. And then chlorine, and we have three. That's it. All right. Y'all have a great rest of your day.